This is a lesson video for 8.1, area of triangles and special quadrilaterals. Be sure to take good notes. Pause the video because in some sections we move kind of quickly and there's more on the screen you may want on your notes. Be sure to add ideas on the side or questions that you might have to ask your teacher about, and then be sure to complete and correct the 8.1 introduction problems. So when we start talking about area in this chapter, we should probably have a reasonable and agreed upon definition for it. Area is a measurement, just as height and lengths and things like that are, but it's a measure of the number of squares of lots of different sizes, but the number of squares of a certain size needed to cover a flat figure. So when you look on the floor and you see square tiles covering the entire flat floor, we could get the area of the floor by simply adding up the number of squares, including adding parts and and counting those to get the area of the floor. We could make circular floor tiles, but they would have trouble fitting and covering that area. So squares fit within the shape and lock together, and therefore we could count the number of squares to fill any flat figure, and that would be reported as the figure's area. So we've had units for measurement already, linear units for things like perimeter. So for linear units, things like inches, meters. Area will be reported in square units because we said it's the measure of the number of those particular squares needed to cover a flat surface. The square's particular size might be inch by inch, so they're square inches. Meter by meter, much larger squares, square meters. When we get to volume and we're working in 3 dimensions and we start trying to get a measure of how many cubes it takes to fill a 3-dimensional object, that would be volume, and those would be in cubic units. All the formulas that we're going to do for area can be traced back or derived back to area of rectangles. You learned area in the beginning likely by counting the number of squares within a rectangle. You could count them, and eventually, because you're quick, you figured out that the base was the number of squares per row, and that was always the same. The height was the number of rows, and therefore a base times height would always calculate the number of squares within that shape, the same as you would get by counting. In Chapter 8, you will have seen a lot of the area formulas before, but being able to derive them, being able to take them back to rectangles and demonstrate how the transformations get them there so we understand where the formulas came from is your proof and your reasoning. So skipping that understanding would be a mistake. So with parallelograms, let's try that out. Let's see if we can describe how some transformations, some reflections, rotations, translations, could get us back to being a rectangle or something we have a justified area formula for already. So I'm going to take you to a GeoGebra for the moment so we can look at a parallelogram. And on that left-hand side, I'm going to take that right triangle that it's formed between the altitude and one of the sides and slide it by translation to the other side of the parallelogram. When I do that, I create a rectangle, and that rectangle now has the same length base as my parallelogram and the same height. So that the same area that was arranged this way is now arranged by translation as a rectangle whose base and height are the same, and therefore its area is base times height. So coming back to something we can maybe annotate, we started with a parallelogram and we translated that right triangle, and it can go to the left or to the right. It could go up or it could go down. It just depends on which way your parallelogram is facing. I translated by a vector straight to the right, a vector the length of the base, which means that initial left-hand point right here would end up here. So this amount of length of that right triangle that it took off on this side, it recreates on the other side. When it does that, it creates a rectangle with the same base and the same height as the parallelogram. Therefore, it has the same area. So the area formula for parallelogram is identical to the area formula for rectangle. 2 goals then. We want to be able to calculate with formulas, meaning we need to know them and be able to work with them flexibly within our algebraic manipulations, but we also want to be able to describe how their formulas are derived, and these are the 3 we'll work on in the next few slides. So triangles. Again, we want to go back to where can I get that back to either a parallelogram, whose derivation I understand now is the same area as a rectangle, or a rectangle itself. So every triangle, we can pick one side to indicate as its base. It could be any of the sides. And a perpendicular to it then is its height. And so going to a GeoGebra to take a peek at this, if I have a triangle and I create an identical one, there is a rotation I could do 180 degrees around the midpoint of one of its sides. And when I complete that rotation, I will have formed a parallelogram. So I'm going to put that back for a second. The triangle rotates 180 degrees around one side of the triangle. And by the time it finishes that rotation, we have a parallelogram. That parallelogram then is made up of two identical triangles. So after I rotate it, the parallelogram is going to have the same base and height as the triangle, but twice the area. So if I have 2 times the area of the triangle is the parallelogram, and I know that parallelogram formula is base times height, and 2 times the area of the triangle then would equal that, you can see where the area formula for triangles divides both sides by 2 and says the area of an individual triangle then is its base times height divided by 2. Trapezoids are very similar, but trapezoids have different variable terms. Trapezoids have 2 bases because the parallel sides are referred to as bases, and typically they're referred to as b sub 1 and b sub 2. And really they're interchangeable as far as naming. And then an altitude between the two is referred to as its height. We can do the same thing with trapezoids that we did with triangles to demonstrate where its area comes from. So let me put the convert slide back. Same idea on a trapezoid, except it can't take the midpoint of any side. It will have to be one of the non-base sides. And when I rotate 180 degrees around that non-base side, then I have 2 trapezoids worth of area or 1 parallelogram. And that 1 parallelogram then has an area of twice the trapezoid. So as we rotate that 180 degrees around the midpoint of its non-base side, we get that parallelogram. The parallelogram has not changed height from the trapezoid, so it would have the same h variable, but now the parallelogram has a base that's longer. It has a base that's the sum of the 2 trapezoid bases. So twice the area of one of those trapezoids is our parallelogram area right there. So then it might not be a surprise that the area of one trapezoid is half that amount, or 1/2 the sum of base 1 and base 2 multiplied by the height. The final one we're going to look at is kites. And in kites, the side lengths can be used to get the area of a kite, but typically the diagonals are more commonly used. In any kite, you know from properties that the diagonals are perpendicular. They create 4 right triangles when you form a kite. So one of the common derivations for getting kite area is to take the kite and to rotate each of its right triangles 180 degrees around that outside or hypotenuse side. And when you do that to each one of those 4 right triangles, their right angles rotate outward, and we end up with a rectangle. So when those 4 right triangles are rotated 180 degrees around the midpoint of each hypotenuse, the result is a rectangle. The rectangle is as wide as diagonal 1, the horizontal one in our picture. It's as tall as diagonal 2 from the kite. And therefore, with twice the area of the kite, because every triangle was doubled, base times height for that rectangle would be d2 times d1. And therefore, the area for a single kite is 1/2 the product of their 2 diagonals. Finally, we'll just do a few examples. Find the area or the missing value for each. So in the first one, they demonstrate to us that we have a kite by definition as the 2 sets of distinct, congruent, consecutive sides are marked. So I can go right to knowing that my area formula is 1/2 d1 times d2. They don't give me the entire diagonal on one of the kite's diagonals. They only give me part of it. But there's another property from kites besides that their diagonals are congruent. It's that that diagonal from the non-vertex angle to the other non-vertex angle is bisected or split in half by the other diagonal. So I do know that that length of 5 repeats here. So I do know that 1/2, the product of one diagonal multiplied by the other diagonal will get me the area for this kite. The area then is 90, and since they don't list a unit label, we're going to say 90 square units. For the trapezoid below, they do provide us the area, but they're very interested in knowing, they do indicate in the problem that it's a trapezoid, and they're very interested in knowing that height or altitude of that trapezoid. So what I do know is that the area for trapezoids is the product of half the sum of the two bases and the altitude, which in this case is x. So I'm going to put in what they've indicated. Area is 63. 1/2. One of the bases is 10, the other is 4. And the altitude we're calling x. This is 1/2 of 14, or 7x. So x, that missing altitude, is 9, and because it's a length, we'd be in inches. Please be sure to go back, repeat some of the problems, or see some of those transformations again so that you have a good complete set of notes, and be sure to do the 8-1 exercises assigned.